One of the key features of DRYAD is providing a unit-based image segmentation. In order to train unit architecture, we need to prepare a set of raster images and labeling data. The blue dot indicates that the input must be given. In this demo video, we will use time series Sentinel-1 images as an input for identifying rice paddy area. The extent of input data doesn't need to be exactly the same, but their cell size and projection need to be coincided. Then, we need to create training validation layer, which separates training and validation area. Before creating the file, the patch size and training percent should be given. And whether the areas are separated randomly or uniformly should be selected. After setting the parameters properly, we can click the Open button to decide where to make the training validation layer. If we already have the layer, we can simply open it. Then, let's click Generate Dataset and see what happens. After a few seconds, a stacked layer consisting of inputs, label, and training validation layer appears to the displayer window. So, if we choose the last layer to be displayed as a blue band, the training areas become a soft blue and the validation areas become a dark blue. If we go back to the unit training window, new interfaces have appeared. The green dot indicates that they are optional, but let's see what they can do. Through the Training Validation Area editor, we can change the training area to the validation area, and the opposite is also available. If we want the patch to become a training area, choose the Training button and right-click the displayer window. In a few seconds, we can see a dark blue patch turns into the soft blue color, indicating a training area. By increasing the brush size, we can change the adjacent patches at the same time. DRYAD also provides a graphical user interface for deep learning architecture design. Here we can see the initial architecture has been automatically set by the size of an input data. The left side of the architecture is for feature extraction, consisting of a series of convolutional and pooling layers. And the right side of it is for restoring the features to the original image size, consisting of convolutional and upsampling layers. Here we can simply add more layers by clicking the plus button, or remove them with X button. Of course, the hyperparameters of each layers can be modified, and the options will be diversified in the future versions. After setting those hyperparameters, let's start learning. If you want DRYAD to use GPU for the training, please install NVIDIA CUDA and CUDNN and make sure they are using GPU statement at the header. Once the unit starts to learn, you can see the loss decreases while the accuracy increases through the graphs. One of the useful features of DRYAD is that it can display a real-time prediction images while it continues training. In column order, there are original images, continuous prediction value, encoded value, and labeling. The upper side is training images, and the bottom is validation images. The displayed areas can be changed so we can get more information on the training procedures to decide whether to continue training or modify hyperparameters or architectures. In this case, the model seems to need training some more. Once we are satisfied with the training result, we can save the model in H5 format. The saving path will be the same with the training validation layer, and its epoch will be recorded at the end of the model name. If the autosave button is checked, the model will be automatically saved when it returns the lowest validation loss through the entire training. In this case, the model seems to be optimized after more than 400 epochs. In order to use the trained unit architecture, let's click the Unit Test button. Here we have to put input rasters in the same order and numbers with the trained dataset. If you don't remember how many layers we have used for the training, loading the model will show its architecture. Then we need to set the output path and batch size. The batch size does not affect the output result, but bigger batch size will speed up the calculation. However, too much big batch size will raise video memory error, so I won't change the default value this time. If we click the Run button and search for the output, here we can see the classification using UNet have done successfully.